Yes, there we go.
Thank you, guys.
We got 15.
I am a computer science major. Okay.
Go.
Wait. Yes, I will. I will. In a second. Wait. What are people's, wait, can we go around real fast? I'm Martine, third year, CS. Yeah, I'm the reading group. I'm supposed to be leading these more, but I've been gone this quarter. So this is the first one. It's calm. It's calm.
Do you have any more coming up?
Yeah.
But if anybody else wants to present, there are open slots. So, oh, you're doing one? Are you? If you want to, you can. We'll post.
I found a reasonably cool like CNN Vancouver paper. Yeah. Okay, cool.
Okay, they're gonna do a reading group in the future. Anyways, our team. Wait, what are new people? Oh,
I'm not
do I know? I see Mark,
Brandon.
Ben,
Alex.
Barangat,
Will.
Will,
Kartik.
Kartik. Sick. Okay, guys, let's go. Let's go. Woo! Okay, so, wait, is everything, Mike, good? Wait, I just want to make sure.
Yeah.
Mike's good. Okay, yeah, everything looks good. Okay. Wait, why does it not?
You're not on the slide. You're on Zoom.
Oh, if I go to the slide, does it? Okay, it doesn't. It's fine. Okay. Yeah, you might have heard about this thing called DeepSeek-R1. This is crazy. This S&P down by 2%. In my mind, it doesn't make any sense why they do that. If you believe in the promise of AI, this is just showing you it's accelerating maybe even faster, so you'd buy more. No, this is no like financial advice.
Are you sure?
But no. You know, that I can speak of publicly. But the thing is, it kind of was crazy. We thought there's this giant moat around US labs, and like it would take billions of dollars of infrastructure. And then it's like, oh wow, you can actually do this for relatively cheap compared to how much the labs in the US were telling us it costed. And then also the fact that it was from China, who we thought we had a giant moat around because we stopped exports of GPUs in like 2022, 21. And it was like, oh my gosh, there's some stuff about like, okay, maybe there's a lot of GPU smuggling. They have billion-dollar infrastructure surrounding it. But like, I'm pretty sure the actual training run was $5 million. You can look at like the amount of like insane infrastructure optimizations they did. Like, I don't think, to be honest, that's really a lie. People are like, oh, they could be doing this and they have more GPUs and they're letting on and they're smuggling. Yeah, sure. But
They
like,
tried a lot.
they
Like there's
did
a lot of GPUs that they did.
Yeah.
That's like beyond what any labs here have been doing.
Yeah. And I think it's kind of the funny thing because it was like we tried to export ban, but then it's put more pressure on them to use the resource as well. So they like optimize like this like to hell. Yeah. But anywho, yeah. So we're gonna talk about DeepSeek R1 and V3. V3 is the base model. So that came out like 2 months ago. And then we're gonna talk about R1, which is the reasoning model trained. So in comparison to ChatGPT, DeepSeekV3 is like 4.0, right? It's the base model, good for just general purpose stuff. The DeepSeek-R1 model is for reasoning, like ChatGPT 0.1. And it's like most people think it's, it's the 4.0. They grab that model and they just train it for reasoning. So it's the same architecture, same pre-training, same general knowledge, but it's tuned and trained with reinforcement learning for reasoning, right? And we're also going to talk about speculative decoding, which is just like a pure speed up you pretty much get by just guessing what you think the next tokens are going to be, and you can accept multiple at the same time. And then Jordan's going to talk about GPU parallelization, which I feel like even here they probably talk about it a decent amount here in some of this stuff. Because to be honest, when you're not running on one GPU, there's a lot of stuff you have to think about. It's not just question.
Speculative decoding.
Speculative decoding. I will get to that, but the general idea is that some tokens might be easier to guess than others, right? If I'm like, I'm going to that's easy.
Yeah.
To the what? Or the answer to the solution is, the answer to the solution, those are pretty easy, is, and then what's the next word? What's the answer? That's way harder to predict, right? But these easy ones, we might not need a very strong model. You need to run GPT 4.0 to predict the answer to the problem. So what you can do is you can use a smaller model, and that can speculate and guess for you. And if it's true, then you can accept like 5 tokens or 10 tokens at once, even in crazy cases. But normally it's like a 3x speed up, like 1.5 to 3x speed up. So yeah,
Another thing, before we start, raise your hands if you know how large language models work. Okay,
Okay,
cool. We don't
okay.
have to do transformers.
okay, yeah. I was gonna do a little. I'll read through it. Feel free to ask any questions at any point. This is supposed to like chime in. This is very discussion based. It's a reading group, not reading talk. So yeah. Okay, here's our little agenda. DeepSeekV3, we got the base model. We're gonna go through what mixture of experts are. Multi-head latent attention, which I don't actually fully understand. You guys are gonna have to help me with that. And then multi-next token prediction. These are just things they did in pre-training, or it's just inherent in the model for V3. This is different than we think most of the other architectures are, like Llama from Meta. It wasn't a mixture of experts, didn't use latent attention, didn't have this pre-training objective either. So V3 also is pretty innovative. Besides the infrastructure and training and optimization and parallelization, they did some like pretty interesting things, which is like, again, very like surprising, again, 2 months ago, but now we're caring about. Then we're going to talk about speculative decoding methods because it kind of comes off of multi-next token prediction. So we're going to talk about a paper called Medusa, one called Eagle1, and another one called Eagle2. Then we're going to get to DeepSeek-R1. So this is when we're getting that model that has all these quirky tricks and stuff. It's a good base model, and we're going to fine tune it with reinforcement learning, RL, to do reasoning. And we're going to just quickly touch on what's called PPO, which is how we normally do reinforcement learning. If you ever hear about RLHF, reinforcement learning from human feedback, what that normally is they use PPO. It's a reinforcement learning algorithm that stands for proximal policy optimization. I should have wrote it there. But it pretty much allows you to tune your models even more. Normally, it's used in RLHF to you fine tune the model to be good at like answering questions and instruction answering. Then you can like tune it even more in a reinforcement learning environment with PPO to get better at responding to humans and non-toxic outputs and things like that. And then we're going to go to the improvement or iteration of that, which is called GRPO. This is what DeepSeek-R1 uses. It was actually introduced in the DeepSeek math paper, where they were trying to train the smaller models in reinforcement learning to not be less toxic or do human preferences, but they trained it to do math, right? And then you're going to see how that's going to lead to DeepSeek, where they use the same exact thing, GRPO, to train it for reasoning. Yes, question?
Is PPO how they censor certain topics like Tiananmen Square or is that where it comes from?
Not really, no. So that's the data, right? The data, you can tune it to act and care about preferences. However, the data is just the preference data. How we apply it is using these methods, right? So like you can just fine tune. So you have a couple stages. You have pre-training. You just train on a bunch of text.
Yeah.
And it's kind of cool. Like you can use some pre-trained models and they just like probabilistically predict the next word. That's literally it.
Yeah.
So if you ask it a question, it might just start listing a bunch of questions and not even answer you. So you need to tune it and train it to, when you ask a question, respond. So what we do in the first stage is, I'll just pull up a slide real fast, or a little image. How do I move this? RLHF. What we do is this image. We normally like explain the moon landing to a 6-year-old, right? What we do is we then have a human write a good response, and then we train the model just like we trained it on normal text. We trained it on actually producing this output. So now it's like decently good, but it takes a long time to write stuff. So what we can do instead is we then have it's now decent at responding. So we can ask it a question, we can get a bunch of outputs, and we have humans rank them. And then we can train a model to learn how to rank like humans. And then we set it up in this reinforcement learning loop and see right there, that's PPO. So the preference data though is collected by humans. Humans have to sit there and say, I think this one's better, this one's worse. I think toxic is better. Don't say this topic, talk about this one, censor this one. They decide that picking. But how we apply those preferences is through this method called RLHF and PPO. Yes. And you don't just have to do this on preference data. You can use PPO to do reinforcement learning on learning or reasoning. You can also do the simpler method that DeepSeek Math used and DeepSeek-R1 used, which is called GRPO, which eliminates some of the complications with PPO. PPO comes from reinforcement learning. there's a lot of stuff you don't really need when you're going to large language models. Boom, good question, good question. Any other questions? Get the lay of the land. And then this is another thing, I should probably said what these are. This is ORMs and PRMs. This is outcome reward model versus process supervised reward models. This is just like you saw with these pairs here. You can just say, I'm going to give this entire output a reward of like good or bad or better. Or you can actually reward each step. You can say, okay, this line was good, this line was bad, right? And we're going to talk about that. So that's a general layout. DeepSeek base model, all the cool quirks. Speculative decoding, which is the, hey, some tokens are easier than others. And then DeepSeek-R1, can we use this RL method? We've used it for preference data in the past. Can we use it to train reasoning models like ChatGPT-O1 or O3, right? And we can actually look what they did because they released the paper, which is great. Yeah. Yes, question.
So what makes this the DeepSeek-R1 training reinforcement learning different than OpenAI's one?
Oh, we don't know what OpenAI the ones is, so
Just like this is all what we expect.
we expect it's probably something similar. Like there's some red herrings, like PRMs, this whole thing of rewarding each process. Little spoiler, OpenAI released a paper called Verify Step by Step. And we thought, oh, like this is gonna be I guess we'll call it OpenAI. We're like, yes, this is it. This is 2023, 6 months before ChatGPT. I was on this ruse as well. I was like, this is how they did O1, process supervised reward models. Little spoiler though, little spoiler on, we're gonna get to a little bit of text. Where'd it go? Where'd it go? Give me a little second. Give me a second. Do I not have it? Wait, did I not have it? There's a lot of math. Don't let it scare you. Right here. They actually don't use this. So they don't use it. They just use a rule-based, they get rid of the whole thing. So we don't know what OpenAI does. We think O1 at first might have done process supervised, but then maybe it actually does. But DeepSeek chose to use another method. So the whole point is we just don't know. We think they're the same things though. They're reasoning models. And this is now the open paper we can actually look at. So like this worked. This actually worked empirically at large scales, right? Because there's a lot of tests. Again, that's what DeepSeek Math was. DeepSeek Math was kind of just their little test. It was like 7B models. And then they scaled it to DeepSeek-R1, which is a 671 billion mixture of experts, right? Okay. Whew. Already a bit of yapping, I think, has happened. But any other questions? This is good. This is good. I think it's good to know the scope we're in. If we get lost in the details, feel free to bring us out of it. Okay, cool. Sick. Okay. Yes, so DeepSeekV3, this came out actually in December 26, 2024. So this is like, like a month or two ago, like 2 months ago. This is where I'm really confused. I don't think you should have stock whatever. Again, no financial advice. But it's like, this is when they announced, you know, they traded for $5 million. What's the Andre Kaparthy DeepSeek tweet? Wait, okay, the Twitter is going a little scary. Let's just wait. Andre Kaparthy DeepSeek 5 million tweet. Is this the tweet? 5.5 is the Reddit link. Oh, this is getting dangerous.
You can upload to YouTube, by the way. It's just.
Oh.
We can show.
Oh, right here. Here it is. Who cares? Who cares? Whatever stuff. Here we go. Yeah. This was when DeepSeek came out. He's like, guys, they trained on 2,000 GPUs for 2 months. And it cost $6 million. Meta, Llama, and like all those massive models, it's like 16K clusters of GPUs or 24K. And it's like 3 months. And it's like just how much more? Like 10x. Like it's crazy. This happened. Yeah, look, yeah, 16x. Llama, yeah, look at that. It's insane. That was 4 or 5D. It's just like, what? That was kind of crazy. Nobody reacted. It was kind of weird. Anywho, that was 2 months ago. That was the base model, which enabled all this. Any question? No, Clark, you look like you're, yes.
Like way cheaper because they like distilled it instead of.
No, distillation has nothing, you think they distilled it off chat, like people are saying that.
People said.
Maybe, sure. I don't know. I think like that's just the fine tune. You still need a pre-train. Like you still need to crunch through those tokens, but like maybe you don't have to crunch through as many. They're pretty, I don't know. Will, thought, yeah.
I'm just saying, like, the 5 million figure, while it is, like, even if it was true and it would be very impressive, it actually doesn't, like, take into account, like, the capital expenditure of buying the GPUs. It, like, assumes you rent the GPUs for, like, $2 an hour, for however long it took. And it only takes into account the final training run. So it doesn't take into account all of the research and all of the trial runs you do, which is, like, very common for, companies that do, like, a lot of, like, test runs to validate their research before you do the final training run.
Yeah, like for them to get to the point where they're like, okay, we can train this for 2 months, is at least a year plus of them trying out different things, running much smaller scale experiments.
Yeah.
Like a lot of times, even for these like big like video models, whatever, it's like, oh, it takes like like a week or like it takes like a month to train. But like leading up to that, they have done so many other
That's
ones
to get the
of
point.
experiments that actually led them to be like, okay, I think we have found the perfect way to train the perfect way to do hyperparameters. Let's do one from scratch so it becomes replicable.
Yeah. But even I feel like even with Llama 4 or 5B, didn't this report the final run as well? Like, aren't we just comparing the final runs, or is no?
Did they report how much it cost?
I think they did. They said how many GPUs hours they used for the final run.
So here, I guess they're just comparing the final runs. It's like even with the final runs,
It's just the final run. That's what I was saying. There's infrastructure around it, but I'm pretty sure the final runs, the cost of final run. I mean, again, the tricks they did, like here, we'll go to the next slide now. The tricks they did FP8 training. They have a MOE ratio of like that much, which is insane for parallelization. A single 4 pass is only 37 billion parameters. Like I think there's a lot of like
No,
I don't.
It's like maybe a order of magnitude more efficient, but I think there are like kind of conflicting objectives here. Like if you're like Meta, you want to like brag about, oh, like we have all of these GPUs, we spent all these hours on them. Like you're gonna flex how many GPUs you have in order to show that like you have a moat, right? It's like no one else can replicate this. But if you're DeepSeek, you want to show that you're a challenger. Like you're like, even though we like don't have very many GPUs, we like punch way above our weight class, right?
Yeah.
So it's like kind of like opposite flexing objectives that kind of
I
like
feel like it's just, oh, we could optimize and care about it, but we have enough GPUs. We're just going to use them versus we don't. Let's like be efficient with it and do like classic China, just like efficient the hell out of whatever you're doing, you know? Like I feel like that's the.
they spend more on like engineer money, maybe.
Yeah. I mean, that's what it, again, we're not going to, so this is the next slide. Yes. We're not going to cover the entire red section here. This is how it's so crazy, whatever. I am not a ML systems person. This stuff is crazy. I was looking at the mixed precision just for a little bit. It's like FP8 train, like,
okay.
What
For-
is FBA training?
So, okay, for reference, okay.
Yeah.
So normally when you do machine learning stuff, or like when you represent floating point numbers, it's FP32, floating point 32. You guys have to see it 33 or like, okay, yeah, but then you will learn, did you know about the IEEE like floating point format? Well, you have like a signed bit.
Like here, look, here,
like that, right? Like, so this represents the possible amount of floating point numbers you'll represent. When you're doing inference for most models, usually you would do it at like FP16 if you don't do any sort of additional extra work. So you will usually train in this, you would do inference here. And the reason for that is because when you're doing training, especially for large language models, a lot of times a certain number, they get really, really big. And when that happens, like because of floating point errors, if say you add a really big number with a really small number, that's different than if you have a really small number than added with a very big number. Like when you get to really big magnitude differences, you actually start to have instances where floating point error legitimately starts affecting your training. So and also if your activation just gets too big, sometimes it's literally outside of the range of numbers that these floating point numbers can represent, and you get an NAM. I don't know if any of y'all have trained networks before and got an NAM, like we try to divide by 0. You can just get that naturally if your precision isn't high enough. So the fact that they could use FP8, which only has 4 exponent fields, which means the number can only represent up to a number as big as 2 to the power of 2 to the power of 4, which is not very big.
16.
That's 16. The biggest number they can represent is 16, and has 3 bits of precision. So like in total, it can represent at most like 256 numbers. Actually, like 128 numbers total.
Yeah.
That's all the numbers you can represent. Just 128 numbers that ranges about from like 2 to the -4 to 2 to the 4. It's not an even distribution because how floating point works, but like that's a tiny amount of number. they can represent, especially for something as precise as machine learning training, we have to do like back propagation and all that stuff. And that's math operations that very easily can overflow and having such few numbers, you have to quantize things to each slot, if that makes sense. So like you don't have the precision of the full like FP32. And because of that, FP8 training is insane because it's so difficult because you have so little numbers you can work with. Like even with Llama 3, they also talked about 8-bit training, but specifically they train in int8, which is they're like everything's an integer. That's easier for them because even though you have less number of numbers to represent, it's a much larger range of numbers. But FP8 is very difficult, and they managed to do it. So you have to do a lot of tricks in between, really being careful about like the distribution of your intermediate activations and like making sure nothing goes as too big, nothing goes too small. And that even if you're quantizing to literally just 1 to 28 numbers total, possible numbers you can represent, you can still do training efficiently and do training with accuracy, which is why that's like insanely impressive. Like people build entire careers out of just figuring out how we can do low bit training to speed up our training.
Yeah.
Yeah.
So I like NVIDIA has something called mixed precision.
Yeah.
And what they do is they do the like forward pass, like they do a lot of the computation in FP16, but they store the gradients, right? The derivative, like in FP32. Because the gradients are going to be really, really small. The slight changes you need to make as they go through the network, it gets very, very small. The FP16 for like, I think that's how it works. That's the general idea. But even then, it's still like you're mixing these two versus just boom. I think they might mix 16 or something. I don't know. But yeah,
Like, it's a lot of engineering.
that's just like one random thing they did. Again, the other thing is that the fact, I'll go to the next one. It's an MOE. Look at these. This is Llama. It's a dense model. And look at DeepSeek. It's a ratio of.
We'll talk about what MOEs are.
We're gonna talk about MOEs, but what this means essentially. So now we'll get into slides. We gotta I think pick it up a little bit. So yeah, DeepSeek MOE. It's MOE. So it comes from efficiency, FP8 training. There's some parallelization. There's a lot of optimizations they have, but I think the big thing.
It's discrete. I mean, all floating point numbers are discrete. Yeah.
Yeah. So DeepSeek is MOE. What is MOE? The basic idea is that the model is 671 billion parameters. That's how many parameters it actually has, right? Like Llama 3, like 405B is 405 billion parameters. And normally when you think 405 billion parameters, oh, I got to run 405 billion parameters for every token, right? But in a mixture of experts, actually, you only use some percentage of them in one forward pass. So in this case with DeepSeek, you actually only use 37 billion parameters of them in a single forward pass. So like it's maybe you could say, I guess, the power of 671 billion parameters with the cost of 37 billion parameters. Again, there's trade-offs and things, but like generally the model is 671 billion parameters, but when you run, you only select 37 billion of them to run, right? That's yes, Will, you have a.
Or there's like
Explain it.
there's like a common misconception that you can run a 671 like MOE model very easily on your laptop because you only need to materialize this much RAM and memory. It's not true unless you want to generate one token at a time because the expert it will activate per token is not necessarily the same. So
There's a lot of parallelization
like
things.
you can do this like during inference, obviously like the compute cost, you're only gonna activate 37 billion frames. So like that means you don't need to do that many flops, but it's not necessarily true that you can very easily run smaller.
Yes, but what it does mean is when you can scale it up to large GPU clusters, it is very, very compute efficient. So that's the difference. So the original OG MOE called G-Shard, they referenced it in the DeepSeekV3 paper. The basic idea is that this is a transformer. This is our transformer right here. We have repeating blocks of attention. Okay, there's a residual, there's norm, whatever. Attention and a feed forward, right? Attention mixes all tokens. This operates on each token, like element-wise, pretty much, and whatever. Yeah, cool. Okay. The MOE, it's not that. The basic idea is that you're thinking, okay, we have 37 billion parameters that are active. So the mixture of experts, you might think, okay, we have 37 billion, 37 billion, 37 billion, 37 billion, until they add up to 671 billion. And what we do is when we have a token, we're like, okay, you're going to go to the math guy. You're the math token. Like you're looking math tokeny. I'm going to send you the math guy. And you're looking like kind of like the science guy. I'm going to give you science. Oh, you're English token. I'm going to send you to English, right? That's like, I think how it's naively explained. That's, I think, a good representation to have. You're sending the token to the expert for that token, right? to process that. And it's, you just route it to which one you think it's best for. But what is actually happening internally is we have these repeating blocks of transformer layers. And what we do is we don't have a whole transformer as in separate places routed to, but each layer, what we do is we replace the feed forward with multiple feed forwards, and then we route to a specific feed forward. So if we zoom into the feed forward, we're pretty much replacing this block with this right here, where we take in the token and we output pretty much like a distribution over all the expert feed forward layers. This is like a dense layer. It's literally like 2 dense layers. That's all this is. That's all this is here too. But the whole point is we split this up, or we make copies of them. So these are massive ones, right? And we just say, okay, this little one layer, I think it's like you just ingest the token and you output distribution over, like if you have 4 experts, you just output 4 numbers, right? And then we just say, okay, you can either weight each of the outputs, or the simpler way, which is what DeepSeek is sparse MOE. You just take, okay, let's look for the highest probabilities. This one, I have the highest probability to be routed here, the highest probability to be routed here. So I'll send my token through that one and that one. And then I'll combine the outputs. And then, yes. Does that make sense? I feel like I didn't explain that well, but any questions?
So for the dense LOE, so you're still running you're running your output through, well, you have like your tokens, you run it through all 4 feed forward networks, but you weight it differently.
You can, yeah, so there's one way, you can dense MOE. This doesn't save you any inference. You have to use all of them, right? This is just like a gating mechanism. Like, can't you just have one big feed forward and implicitly it learns this circuit? Like, yeah, like this isn't really worth it. This is the main benefit, is that I actually only take like the top 2 and then I weight them. And then I'm actually not using 2 of the feed forwards. So I just have to compute like 4 feed forwards, right? But I could still have it like each one of these as big as the original, so that's the basic idea.
It's just like a softmax.
Yeah. Oh, you're stretching? Yeah. Question. V3.
Yeah.
So V3. We're getting to it. We're getting to it. Okay. I just wanted to say, this is still G shard. We're on it again. This is, if you look at V3, they're going to reference G shard. This is how they do it. You can actually then split each feed forward onto a separate. If you have multiple GPUs, say 8 GPUs, and you have 8 experts, you can put a feed forward expert on each of the GPUs. And then when you get to the gating, and it's like, oh, this token needs to go to the first guy and the third guy, you just route across GPUs. So this layer, yeah, that's what you do. You don't have to. Yes, that's it. That's it. You shard. The whole point is you're doing some sharding stuff. Yes, Jordan will talk about things like that. Any questions? Yeah, you have a different feed forward on different GPU. It's just parallelization optimization. But you can see how this is kind of efficient, right? Before we had to either hot swap in out in a single model, we have to hot swap in feed forwards. But now we can run pretty much like 8 times the amount, but we're of stuff, and we're not even underutilizing, like it's all
And the amount of memory that you need to put the model in the GPU has just been reduced by a huge amount.
Yeah.
Because you're putting only like, if you have 8 mixture of experts, for example, you're only putting roughly an eighth of the model in each of your GPUs.
Yeah. Again, it's the main idea of just this. You're only using 37 billion or whatever, which means you can divide that, do math. Yes.
And if you really want it, you can also just like offload each one of those modules onto your CPU. If you really want to run on a single GPU, you can offload on CPU and then put it back, but that takes a very long time.
Yeah, that's what you would do if you had like on your laptop. You wouldn't have enough memory to hold the whole thing, right? So what you would do is, this is the annoying thing. It's not just you load a single model for a single token. Like each layer, you'd be hot swapping out. It's not 37 billion, but you'd be hot swapping out a different feed forward. You're like, okay, I need to route to these tokens. I couldn't fit all the feed forwards in all the experts in my memory. So now I have to go back to main memory, and which just takes a long time. And I have to go, okay, I need this layer and this layer and this layer, put it in. And then I run those and I go through the attention. The next layer, oh, I need to route to those guys. I can't fit them all in my memory. If you could fit them all, then okay, but you can't fit them all. So then you're like, oh, I gotta go. And it takes a lot.
Go back to the CPU, come back.
Yeah.
CPU GPU bridge takes a.
And versus with multiple GPUs, you can have it. I know that guy has it. He has it in his memory. I just have the first feed forwards. I have all these feed forwards of F1s all the way through all the layers. So then therefore I can just send it to the other person who can handle it. Right. That's MOE. That's the basic idea. And that's why you see stuff like this where it's like only active. By the way, I think people think GPT 4.0 and I guess 01 is like a 1 point, where did I put that? It's a 1.8, yeah, like a 1.8 trillion parameter model with a 200 billion active. People just think, I don't know why. Maybe some reasons, computation. Any,
Size of model like directly like correlate with it being better.
no.
Well,
Yes and no. Yes and no.
that's
no.
a whole other discussion of LM scaling,
Yeah,
which is,
you
Oh.
hope it is.
you hope
right?
it is.
You hope it is. You
Yeah.
do the little dots and then you.
The
Go
trend
big
so
one.
far seems to suggest that it is.
But
But-
I mean, pre-training and text.
Yeah, so that's a flop, or it's like, you can use more flops to get a so much a smaller model to like a better floating point operation. Like you can train small model and more tokens and it will, you can push it beyond the chinchilla efficient frontier. But the
Just drop that. Just drop that.
like in general, like larger models, generally you see them that you see them have like better like knowledge storage. Like they will store more factoids. But it's not necessarily true that they're better. It depends on how much training compute you set.
Yeah.
It's one thing to store them, it's another thing to know how to use them. Yeah.
So yeah, training also versus inference is a big thing. Test time compute. I mean, these are the reasoning models. Hey, wait, maybe we don't spend as much time training. We could just have it run longer and get the same accuracy on some benchmarks, right? There's that trade-off as well. And a lot of cost is in inference, actually, not even just training. It's hosting all this. See all the rate limits for DeepSeek and Claude, and it's like, oh wow, they're literally just burning money serving models.
Yeah, so really the capabilities of LLMs is like it's three axes. The first axis is how big the model is. And the second axis is how much data you're gonna be training it on, kind of how long you're gonna be training it on. And the third axis is how much during inference are you willing to let it like be able to think and
Yeah,
do this
That's a
work.
new axis which we
Yeah.
didn't have before. Now this is the year we're actually getting in that.
Yeah.
So yeah, MOE. Now this is now DeepSeek MOE. So with DeepSeek,
Well-
Alex's question. What they do is they actually don't have just however many experts. They have some shared experts. So these always get used, right? And then they have some routed ones that they route to. This is the math for it. This is just saying what we do is we get the token, we pass it in. This is our router right here. And we say, okay, the top K of them, it's the same thing as the sparse MOE, right? We pick the top K, this is top two probabilities, and we route it to it. And then I think the shared are always shared. So this is the number of shared. I think this is always used. I think that's always used. And then this is the number, which is this the G of G, which is the dated one, which is the non-shared, which is the routed, I think. Anyone wanna look at this and help me? Yeah, but I read more details. The ratio is they have just one shared and they have 256 routed. So I don't know why they even have one shared. I think maybe the one shared is bigger. I don't know. I haven't looked too hard. There's a lot of stuff in the paper.
So the idea, like, you wanna remove like some redundancy where they shared like does like maybe something that they all should be able to know, but not it's like some bit extra.
Sure. I don't know why they did that, to be honest. DeepSeek V3. Do I have the paper down here? Actually, I think I have the paper down here. No. Yeah, it's G#. Paper. No, you're gonna bring me the Okay. We can check. Yeah, I don't think they say, to be honest. Yeah. I don't think they say why. Oh, they probably do, maybe somewhere. I don't know.
I have like a hypothesis, or like here's like a hypothesis based on like the MOE scaling last paper that came out a while ago. So like it turns out that if you just do sparse MOE and you scale the number of experts, at some point you get like expert collapse, which is that like you will just not use some experts.
And yeah, I will really skip like in the even with auxiliary load balancing and all the
Yeah, like or like in order to prevent the collapse, you will need a stronger and stronger auxiliary load balancing loss. And what this loss does is it makes your model worse because more of the routing layer is like being regulated by the loss.
yeah. So yeah, I'll explain that. That's actually in the next slide. So 2 points. We know what MOE is. We're now looking at DeepSeek-R1. So what does DeepSeek do? DeepSeek has this ratio and it has one fixed. That's the main thing to take away. And the second thing to take away is that a lot of previous mixture of experts had to do this thing called auxiliary load balancing, which is what we're talking about. The model has all these options, it has all these options to go through. In which this learns when should I get it to? And it's going to learn that through backprop of like, I should gate this token when I see this token, I should route it through this one because it was better. It led to better performance. But let's say this one gets trained more first. Then it's just overall better. Then the gating will learn, hey, I should always route to this guy. These guys are bad. Like this guy's trained more. And it'll just only use one of them. And the rest will be really poor, right? So what a lot of them did is they introduced a loss function which says, we're going to subtract the loss if you are using these other ones. But it's like an auxiliary loss. So besides the normal loss function of like, did you predict the right token or not? We add a loss term of, are you using all of them evenly? But it's a little finicky and kind of tweaky, right? So what's kind of cool is that DeepSeek, what they did is they actually just said, okay, we're going to get rid of that. And we're just going to add a bias term that we increase or decrease. So that's this B right here. Just like right here, where we select the top probabilities, we add this bias term. And what this bias term is for, each expert has a bias term associated with it. And what we say is we say, hey, if you are using this one more than others, we're going to decrease your bias term. We're going to make it like more negative. We're going to say, don't use you as much. And they're using us that expert more, we're just going to increase it. And that's it. And the amount we increase or decrease is decided by some like, that's it. Very simple. Like if you're being underused, we're going to increase the amount you're being used. And if you're overused, we're going to decrease it. We don't have a loss function that's auxiliary and all this, like whatever. They just add a bias term per expert. And they have it be able to increase or decrease by like a linear amount per if it's above or below. Like it's not even a PID, it's a P. Yeah, that's it. Or not even P, it's just a constant. If it's above, it's a sign, yeah. Or not, yes, whatever, indicator. Yeah, cool, yeah.
I'm actually
Question.
curious to see your intuition on this. So like, I feel like intuitively, it's like you're not hamstringing the routing layer to like just try and distribute the load evenly. Like you still want the routing layer to like decide that like a certain expert is good for like a certain task. Like you actually, you don't want to penalize it in the gradient space. But you do want it to like effectively have like in your large batch, have the average case behavior where like the most experts roughly even, right? So
that sounds right. Yeah.
Yeah.
I like that. I like that one. I don't know. I think it's just like overcomplicating it. And it's like we want to put this is like classic bitter lesson. Like you don't want to force constraints on this. You want to let it learn, and we don't want to have to incorporate this loss and make it all complicated. We just want like the minimal thing. We just want it to be able to evenly use them, but we don't want to hurt it in any way. Like the minimal stuff we can do and just let you learn, I think that's my perspective on it.
It's like only used during pre-training, right? I don't think.
Yeah, once the bias is learned though, you have to use that bias at the end, because that's the bias term you've learned over time.
When you're doing reinforcement learning, would you still change the?
They might freeze it. Actually, no, they might. No, I'd say to freeze it. Yeah. The gating layer, they might even fully freeze. Like, I don't know.
wait, what was your freeze? Wouldn't you want it to
Yes,
as many degrees of freedom as possible?
maybe, but it's just this is a little complicated. This gamma, I'll show you the training, what they do, and it's like they go up, down, left. Okay, faster. Okay, so that's just one part. That was just MOE and DeepSeek, but that was a lot. Like we introduced MOEs, and then we also talked about what DeepSeek was doing with MOEs. There's a second thing. So this is the V4s. These V4s, we went and we said, okay, we're gonna do this whole MOE thing, and that's how it's 37 billion active parameters and 671 total parameters. But there's other cool thing called multi-head latent attention. There's no one else. I don't think so. I think some other people are doing it, but this is crazy stuff. This is some crazy cool stuff. So I'm gonna have to not introduce all of it because there's a lot. But the general idea is that when you're doing like generation, like hello, my name is blah 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 blah. What you have to do is you have to do the attention operation. In the attention operation, when I'm producing this new word, and I have this new word, and I want to predict the next word after it, I have to go to the self-attention layer, and I have to attend my query to all previous keys. And then once I get the attention scores, I have to multiply by all previous values, right? And these values are calculated by ingesting the token and projecting them to key and value, key and value, key and value. And you have to do that for every time. This is multiple layers. This is a single transformer layer. The models are like 96 layers, you have to do this many, many times. And you have to project all the previous tokens. You have to do you have to protect them to the keys and values, and you have to do this attention operation. But what we found is actually you can cache the KV values, the key and value values. So what you can do is like, I know I computed like the projection to be this KV and this K and V for this token, and I did it for this token as well. And because transformers or GPTs like are autoregressive, they have a causal mask. This token, if I have a new token or it happens up over here, it can't see this, it can't attend to it. So this token stays fixed. We can cache it. This does not change based on any future token. So what we normally do is we always KV cache our values. And this leads to a great speed up because you're not going and, okay, I'm going to process this new word token, I have to query and attend to all these and I have to recompute all the context. Like, no, these are fixed. You still have to do the attention with them, right? So you still need to be able to store all of it, and you still need to, like, it's still linear. If you increase another token, you're going to have to multiply it by all of them to get the whole attention and do softmax. But what you're able to do is not have to do the recomputation for all, right? So it's just better. Like, this is a big thing, KV cache. And it's not just your context. It's not just the words you're filling up. You're technically filling up the words, and then there are KV caches in all the layers. That's what you're storing as your length grows. So you process the new word, this new query, and you're doing the attention with all the other ones, but you're also, while this query or this current token is being processed, you get the query key and value. The query you use to attend and all that, but the key and value you just keep there. And then when you get to the next token, since you compute the key and value for all of them, you can reuse those, right? That's the, yeah. Question.
How does latent?
So latent is really interesting. You need to store the keys and values for all previous tokens. The general idea, again, I don't understand it. You guys help me pull up the paper, DeepSeek-V3. What they do is they say, okay, this key and value, what happens if we actually compress both of them into a single latent vector? So we get the key and value for a single token, and we compress it into even smaller latent representation. So this means you don't need as much memory. As your context grows, you actually don't need as much memory because you're compressing your KVs. And now Jordan's interested in that. That's the idea. That's the idea. You normally have this KV cache that you're building up, and this actually limits how long your context window can be, right? You know, there's training and it's not used to larger context windows, but like your laptop, you know, it's going to fill up. So maybe it has to throw out half the model weights to make it so it can go long enough context, right? This is the idea. This is the basic general idea. You want to look at the math a bit? Yeah, just read. The core of MLA, multi-head latent attention, is the low-ranked joint compression for attention keys and values to reduce key value, KV, cache during inference, right? What I just said. What is C? What is CK? CK is a CK is the compressed. So yeah, what you normally do is you get your hidden, you grab that and you project it to your Q query, key, and value. What they do instead is they project the hidden into a compressed space, right? And then, wait, do they? Yeah. And then from that compressed space, they uncompress. So this is down compress. See, this is down compressed KV. So they get the hidden and they compress it downwards into a compressed space to be a representation of compressing the KV. And then when you want to actually get the query out of it, you up project it to get your query or key, and you up project the same exact latent, same exact compressed representation to get your value. So this, instead of having a key and value, you have just this crushed down latent and you extract from it.
Wait, so okay, so in this case, you're kind of like, so you have additional weights that all it does, all its job is to compress and decompress these latents.
Yes.
So it's kind of like you're training a mini autoencoder.
Yeah, like, and you're making it aware of pre-training. Like you're not just doing this post like, okay, we want to have this little encoder.
You're doing this
You're doing this. This is what you're doing.
Okay.
You're doing this throughout the entire thing.
Okay.
Yeah. So from the start, it's not like, okay, we have a LLM, we could learn autoencoder compress. You know, we're gonna do it during pre-training, so it's very aware. It's built into it. It's not like some hack. Yeah, there's some stuff you gotta watch out for though, because like the rope positional information and stuff, it's a lot. I'm good. It's too much. Like I think I have a. Do I have another?
Okay. Do we want to talk about rope?
No.
Okay.
No, we don't.
Rope is basically a way to do add positional embedding.
It's-
Do you guys know what position
No,
embedding
that
is?
during
LLM. So it's just a fancy way to do.
it's an embedding. Yeah. So you need to know the positional information of the tokens, but they try to preserve that by doing some extra stuff.
some complex number
I
weird
think
stuff.
they like extract it. Like, look at this. This isn't just a simple latent KV, but they have the applied rope to the K that's here before it, and then stuff. Again, I thought I understood, but I did. It's okay. Yes.
If you go back to the previous slide, I'm pretty sure the KRT is not actually like, I think that is literally like the addition or something. Like that's like not like K.
So they're
You
using.
concatenate it. So
Yeah, like your concat, like,
Oh.
I'm pretty sure, or I think KRT is just like it's like the rope. Wait.
What is it?
Oh, okay. I know why. Okay, so
Go, Jordan.
what's happening is, okay, and every single time you have to do this sort of like projection thing, you need to apply your positional embedding, because that's how you're telling the token, oh, you're position 3 and you're position 1, you're position 2, right? So what you have to do is, because the new token that just came in doesn't have a positional embedding yet, you need to apply positional embedding just to this token. These, when they have been compressed before, already has this positional embedding information, because what you would do is, as you're generating things, you're going to apply positional embedding, and you're going to take this and you're going to do your KV and compress into it. So basically you're saying, for my current token, I'm not going to let it go through this whole compression process, because that's stupid, right? Like, I have this full information. Why am I feeding it through this whole compression process? So all these previous tokens already has rope applied to them beforehand.
Oh,
So you only need to do rope on the most recent token that you're dealing with.
But is that rope information stored into your compressed cache?
Yes, I think that the
No,
data
not
flow
No,
is.
because are these the ones being cached? Because
Yeah, well,
if
well,
these
these
are-
are the cache KV, right? So here
but then that means these cache KV never got the positional information.
well, the thing is that these cache KV got the positional information in the previous iteration when you're iteratively generating it.
No,
Before you
this
put
doesn't
it-
make sense, because rope is relative, so your rope matrix should change at every position. You actually don't want to.
Oh,
have,
that's
like,
fair.
Yeah, so like, I actually think, I thought like, this is actually a really clever observation, because the KV cache we're storing doesn't include the relative positional embedding, because it wouldn't make sense if we
That's
did.
fair.
So we have to like reapply the positional embedding at like each step. I think, yeah, KT, what's a KT? Why do you only apply it to like the
Yeah, because you also only apply rope to the current token. You don't apply to the previous tokens for Q either.
Let me see the next slide.
Now-
Does this oh, also they do it for the queries, they do something. That's cool.
Oh, they use decoupled rope.
Oh.
Oh.
Well, that's why that's
Oh,
Oh, okay. Interesting.
oh.
So I guess that's how they're able to apply them separately.
no, but if you have this stuff in your cache, do you have to then, when you're doing it, append the positional? I guess that's what you do. When you decompress it, you like decompress the thing, and then you append what the positional should be. 'Cause that's decided. It's not really computation. You can maybe do that easily. I don't know.
That's fair.
I don't know.
I don't know.
Anywho, you guys, there's some fun stuff to go read if you want. But yeah, that's the general idea. Again, cool stuff. There's a lot of stuff to cover. Yes. Anywho, more stuff. They do stuff with the queries and they compress them a little bit as well. Ultimately, are combined to yield the final attention output. Yeah. Wait, Q? What do they do with Q? Which can reduce activation memory during training. Again, like this is not, I don't know. Maybe there's some papers on it, but it's like this is pretty innovative, like this new interesting stuff that they're doing. And here's the next thing. This is another thing they did during pre-training. They did, again, like going back to this, like they did some pretty interesting things. They did this multi-head latent attention. They did this like auxiliary loss free load balancing with this bias term thing. They also have this other thing called multi-next token prediction. This is all in pre-training. This isn't some like hack afterwards. They do this in it. So this is the basic idea. Wait, what did they call it? Multi-token prediction. Not next token, whatever. This is your normal LLM. You have some like text and you want to predict the next word and you can do it all in parallel. For the first word, you can predict the second word, second, third, fourth, fifth, because it has a attention mask. You can do it all in parallel. Beauty of transformers. Great. What they do though, is they say, okay, we're actually not just gonna have the objective be predict the next word. We're gonna have the objective be predict the word after that. For this given token, for example, don't predict that just the next word T3. T2 should also be able to predict T4, right? And then also T5, right? And you're like, okay, how does it do that? Like it needs to somehow do computation. they say, okay, we're just actually gonna have train these called next token prediction modules or multi-token prediction modules, and they're just single transformer layer. This is very reminiscent of Eagle, which we will get to.
It's got a tiny little
It's a
layer right
single,
before
it's a
the
single
output.
transformer layer. This is like a bunch of blocks. That's what 96 layers. That's what most like big transformers are. This is a single one, and all these are just say, okay, like, can we somehow like get more out of our data? Maybe this has a stronger gradient signal that goes back to the main model. Because if this model can like pre-plan about future tokens, maybe it's like it can learn better and more densely from information and faster, right? Also, though, it lets us do the speculative decoding, right? Because if we have these little modules that can predict like the second and third token, then we can actually, and they're just a single block, they can run really fast and guess the next second and third, and really computationally quickly guess the next token, right? More math, but inspired by whatever, blah, 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 extends to predict multiple future tokens. On one hand, the MTP objective densifies the training signals, right? And may improve data efficiency. Yeah, question? No. No question, yawning. But yeah, like that's what I just said. I think that's kind of true. Maybe if you're making the model have to think about predicting multiple tokens as well as the main one, the next one, then maybe that's true. And then on the other hand, it may enable multiple pre-planned representations to predict future tokens. And yeah, output head, we sequentially predict additional tokens, whatever. Yeah, that's the basic idea. Running out of time a little
It's
bit.
1 p.m. Just
Yes. So they also here, okay, yeah, those are the three cool little quirks. We're gonna now just say, I just want to wrap it up. I'll show you what they do for actually training, wrap V3 up. This is what they do for like training. Cool. They go 14.8 trillion tokens. Llama was like 15 trillion, I think. So that's the comparison. They do fill in the middle, which is another pre-training like objective, which is allows them like code completion or like you have code above, code below. What I do in the middle, it's a causal model. It can't predict the middle if this stuff down here it can't see this stuff when it's predicting it here. So what they do is they really grab the prefix and the suffix. So they grab the beginning end text and they say predict the middle text, and they add that as an objective so it can do infilling for text, right? Meaning like code generation, you can just like based off the context above and below the code, right in the middle, right? They use byte pair encoding, standard stuff. Pretty much just they make 128K tokens. That's the TLDR. Yeah. Any questions? No? Cool. Yeah. It's cool. I like looking at like this is really nice. I love when they detail it all out. They have 61 transformer layers. Hidden dimension 7,000. That's cool. They talk about the MLA ratio, which is like we have 128 heads, just normal attention heads, and then per head is 128. That's pretty standard. KB compression dimension and stuff is like 512, and then that's cool. And then this is where I found the thing about MOE. They have one shared expert and then 256 routed. And I don't think there's anything else really much there. And they have 8 experts
Wait,
activated.
does each layer have distinct routing?
Yeah, but that's MOE. What do you mean?
Wait, every
That was my point here. Like experts are not entirely separate. What do you mean?
gotcha. Sorry.
They're not entirely separate transformers. Despite what people think, they're at each layer.
Okay.
Each feed-forward layer is replaced with it. But each feed-forward has a separate one. Yeah.
So they're constantly mixed back together.
What?
So it's like at each layer you can actually pick like different.
Yeah,
experts.
each layer. So it's not just I pick this one path in the beginning and I run through this whole transformer. It's I can like a brain a little like ooh, not trying to too
Right.
neural inspired, but you can like route and then I'm like, oh, I want to go this feed-forward. I want to go this one. I want to go to multiple. Yeah.
61 transformer elements.
Yeah, I guess. Yeah, you can
Yeah.
choose where do you route to. Again, dense networks kind of probably did this implicitly. Like they did the computation, like I'm gonna care about these features and this, but it's like maybe you don't need to actually have them doing that computation. Like maybe a lot of it was like low rank or something. So yeah. And they say, wait, we're intermediate representations of experts. Among the routed experts, 8 experts will be activated for each token. And each token will be ensured to be sent MS 4 nodes. So that's like actual compute infrastructure stuff. multi-next token depth D is set to 1. Oh, they do just the next token prediction. They don't do more than that. And then, yeah, that's it. And they said based off the setup, 671 billion parameters, 37 billion active. Cool. Yeah, go read the paper. Pretty cool. DeepSeekV3. Okay, so okay, we got the V3. That's a lot. Like that is like, to be honest, like the most modern pre-training that detailed you're gonna get with a bunch of cool quirks and techniques. So a lot of stuff, a lot of stuff. Now we get on to speculative decoding. This is cool. I think this is just super smart. It's exactly what you just do. I don't know how we didn't think of this. This is the stuff. And again, it's gonna this multi-next token prediction. You're gonna see a little stuff kind of overlap. There's a reason they did it because they realized speculative decoding is the thing. So this is speculative decoding. The idea, the basic idea, is that some tokens are easier to predict than others. So right here, Jeffrey Hinton did his PhD at the University of is pretty easy. You can use the small model, whatever. But then it's like, where do you go? Oh, the actual. Oh, let me think about that. That's a difficult problem. This is a little animal farm AI generated. All tokens are created equal, but some tokens are more equal than others. And I have this. I generated all these with Sora. This is the beauty of AI. Anywho, moving on. So yeah, the basic idea is you have a smaller model, like a 7B, and you have your 70B model, right? Like, okay, I can run this sequence, like the quick brown sock jumps, whatever. I can run that through my big model and just do next token prediction. But if it's like easy words, jumps over, like overs are pretty easy. I could guess that, right? Then you don't need the big one. Use the small one, right? But you're like, okay, but I still want the power. I still want like some way for the big one to check. Like I don't want just a trade-off of running the smaller one, right? I don't know when to maybe use the smaller one or use the bigger one. Like, how do I reconcile this? So the basic idea is what we can do is we have this assistant generate. Like, let's say it's 70B versus 70. That means this guy can run 10 forward passes in time it takes like this one to run once. So we can generate 10 tokens, right? But they're like, are these right? Are these good? What's beautiful about transformers is we can pass all of these tokens in from here into the big, like our main transformer. And because of how transformers work in the causal attention, we can check all of them in parallel. We can process all these tokens in parallel. Just like in training. In training, what we do is we train off all the tokens, we pass them all through, and they each predict the next token. That's the beauty of transformers. They're parallelized in that way. It's not like RNNs, you have to wait for it to go, right? But that means for training, we have it. We have the whole text, we can do all of it at once and do next token prediction, and then we can back off. But at inference, we don't have the future tokens. We have to wait for this one to come out to put it here to predict the next. The idea with speculative decoding is we just have a small one, generate them really fast, and just fill up our window, and we can pass them all through. And if all of them are wrong, we throw all the answers away. We don't use any of it because the model guesses a bunch of bad stuff. But if the model like really quickly went through a bunch of them and we pass it, and the first couple words are right, let's say the first word was the next word we're going to predict, then we know instantly the second one should be it. Because if the small model guessed the, or it guessed from the, it guessed quick, and we put quick here, we already put quick there. So we know the next word, right? Like we put the, we processed it, and it turned out to be the next word we should predict from the is quick. It happened that our speculative model also guessed quick already. And while we were processing the, we were also processing quick, which means instantly when this one forward pass, since we see the, and that's what our model predicted, then we can also accept quick, and so on. If we saw quick, then we're like, wait, we already guessed quick, and we put it in until we have a mismatch where our speculative model, like sock, the quick brown instead of fox, it guessed sock, and then we can't predict it, right? So we can't accept that. We have to reject it, right? I'm not sure if you guys can see a little, yeah. We have to reject it, but we can predict. We can take the main model's next prediction and actually use it. Does that make sense? I feel like that wasn't well said. Yes.
Why is it easier for the main model to verify rather than just generate its own?
It can. It's just way slower, right? The bigger model is always better. Use the bigger model, go ahead. The thing is, let's say this is a 7 billion parameter model. This is 70B, 7 billion parameter model. This is 10 times faster to run, right? If I can I can generate one token guaranteed at a time, take seven units of compute, let's say, right? Versus I can generate one token at a time, also, but now at one unit of compute, right? The idea is, if I'm always wrong on the first word, and I generate a bunch of tokens, I generate 7 next words, and I pass it in the model, I'm like, go ahead, predict the next word. And if the first word's wrong, then it's not worth it. It's just like, what are you doing, right? But if it happens that at least, well, we use 2 of the words are right, then there's no difference. We're good, right? 2 of the words are right. Then what we could have done, we generated 7 words. That's pretty much a single forward pass. So we should have just done the forward pass, and there's no difference, right? But if the 3 of the words are right, we just for 7 compute, we got 3 words. Because we have to spend 7 verifying, then 7 speculating, then 7 verifying, right? Is that kind of?
I guess my question.
Sorry, what? Yeah.
I guess my question is, why is verifying take 7 compute or whatever? Rather than, and why would generating it be so much more expensive than verifying it?
So verifying it, you can do it all in parallel. That's the beauty. You can process all these tokens at once. That's the main transformer benefit. When you're training a transformer, you have all the tokens laid out. And what's really cool is that let's just go back to this. Like, ignore all this stuff. This is the transformer. You can put token 1, 2, 3, and 4. Like, hello, my name is, and you can pass it all in at once. And in one pass, take 7 compute, it doesn't matter. These are all happening in parallel, right? You can do the next word prediction, which is the beauty, because there's causal attention. The attention says, this token actually can't look at this. Like this word is not able to look at this, and this word can't look at this, and this word can't look at all this, and this word can't look at this next stuff. Which means you can process it all in parallel, and it works. Versus like older architectures like RNN, you couldn't do the processing of this because you didn't have the hidden intermediate state from this computation. So you had to go through, then had to go through, and had to go through. Transformers can parallelize in training. Inference, you can't. You don't have this next word. You can't predict the next word if you don't have the next word, right? You can't say, what's the next word after this word? You don't have anything. So you have to wait for, oh my gosh, you have to put the word the starting token. You have to process all the way through the big model, get it, and append it. And go all the way to the big model and append it. It's like, man, that's really annoying. What if we just have a model just like spam a bunch of stuff and we can pass a bunch through? Maybe it's all wrong. The first one will be right because it's just what we were going to do anyways. But like, why not append some stuff to just check in parallel? And if it's right, we can instantly boom, 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 accept it, right? That's the idea.
So it's not really any more computationally efficient. It's just if you have a bunch of things you can execute in parallel.
Yeah.
Why not?
Why not? Yeah. Yeah. But again, you are trading off of this. You have to wait for this to do the passes. So
but it's much smaller.
It's much smaller, but you need to win out, right?
Yeah.
You need to it needs to be worth it. If you're generating a bunch of tokens and you don't accept any of them, then it's not worth, right? And okay, maybe I make a bigger speculative model, but now it's costing more, but it's accepting more of the tokens, right? There's more hit rate. So it's like a balance between it. Anywho, this is kind of hard though. This is kind of hard because you need a smaller model that the distribution of how it's speaking and what it's outputting matches the larger model. Because if it doesn't, then you can't accept it, right? So you need to, like, if you fine tune the big model, then you have to make sure you have a speculative model that's fine tuned as a small one. And it's like, this is kind of annoying. You know, and you want to have these 2 models running. It's a little bit much. It's a little bit much. So we've gone better than this. One of them, early on, Medusa. It's like, hey, why are we using a entire 7B model for 7B model? Why are we using a smaller model for it? It takes too much time. Let's just train a single linear layer, just as the LM head for the normal transformer just predicts the next word. We'll train a single feed forward layer, right, to just predict the second word and third word and fourth word off the last hidden feature. Very simple. Like literally all it does is it just adds heads, like Medusa. That's the idea. So yeah. Instead of using a smaller LLM to speculate, you don't even use an LLM. You just use yourself to speculate. Yeah, it makes it very quick, very cheap. But you can already see some problems. Well, actually, we're not going to get the problems yet. We're actually use something pretty cool. But which one do I pick, right? Like I have a sequence. I have multiple predictions, right? Which ones do I put in my window to check, right? Like even here, I could predict quick, I could predict another word, I can predict whatever. Which one do I choose? Just the top one, I just greedy sample, just one sequence that I pass it through. What's really cool is with attention masking, you can actually do multiple sequences. You can do multiple guesses for the first and second and third. So in this case, we do have multiple guesses, it's very clearly independent guesses. And what we can do is we can just try every combination. And we do attention mask. So what this looks like is, do we want to use it or I? I don't know. We'll just use both. We'll use it, and then we'll use I. And I won't attend to it, right? So what we can do is we can check it all in parallel. We pretty much, this is what the actual window looks like. This is like what we pass in. It looks very weird. This doesn't make sense. It, I, is, like, quote, the, is, that doesn't make sense. But in the attention mask, it does. If we look at any entry, it just looks like we're saying it, or we're saying I. In this case, is, we're saying it is. This case, we're saying it apostrophe, right? This case, we're saying it, the. In this case, we're saying I is, right? With the attention mask, we can pass, this is what the sequence looks like. And if we make the masking look like this, we can actually check many, many, many different sequences all at the same time. Yes.
Isn't this efficient because you're still computing the attention scores between these zeroing them out before the softmax?
Wait, say that again?
Like if you have like this or 8x8 matrix, you're still calculating 64 attention scores, you're zeroing out.
Sure, but you're at inference, and at this point, the whole point is like you want to parallelize more. Like think how much you're parallelizing in training versus inference, you're literally using one token, right?
Would you rather like try to concatenate these along the batch dimension instead of the sequence like dimension? Makes sense. Let's go.
No. Because, well, you want, let's say there's a massive context over here that's verified, you want them all to share it, right? In which case you have to data
Oh,
pair it, like,
well,
this is the same, I think it's like you can optimize tree masking to be like that. Depends how you want to shard tree masking and do all this stuff. But the general idea of this is called tree masking. It looks like a very awkward sequence, but it's actually checking all the sequences at once, right? And so what it'll do is it'll predict the next word for it, and the next word for the sequence I, the next word for the sequence it is, and then you can check like a bunch of them all at once. So like instead of just predicting, like checking one, we do this weird packing, and we check like many at once. Yes.
Are the check marks ones, the basket,
The check marks are yes, ones.
and then everything else is a zero?
Technically,
but
everywhere
where is
else is a negative infinity, which is added onto the attention mask. So you can think about it like multiplying by one, and then on these places, and then everywhere else zero.
Oh, okay.
So yeah, ones, everywhere else is zero. You don't attend to, you can't look at, right? Yeah. Problem though, but also it's really cool. You can speculate with your own self in the head. It's like these are independent guesses. Like if I pick it, like this distribution would change. I pick I, this distribution should change, right? But the whole point is they are independent and they're very cheap. You want this conditioned on whatever that is. I feel like you want some kind of autoregressive. Wait, now we're getting back to just using smaller LLM. So we're like, oh, I want a very quick, cheap way, but I don't want a whole 7B model and train it. It's very cumbersome. Like, what's some like in between? Enter Eagle. It's the best of both worlds. Wait, it's hiding it's the best of both worlds. Hannah Montana, there you go. It's the best of both worlds. In that what we do is we don't have a head that just predicts the first, second, third, and fourth word. What we do is we have pretty much like our draft model or 7B model. It's now just a single layer, but it works like Medusa in that we allow it to use the features of the larger model. That's the idea. It's a single transformer layer that does the autoregressive prediction very, very fast, but is allowed to use the really rich features from the main model. That's the idea of Eagle.
so how's this distinct from Medusa?
This is distinct from Medusa. Medusa is not autoregressive. Medusa has independent heads which use the hidden feature, but just predict these independently. Like this is not autoregressive on this. Like this distribution is not dependent on. These are all independent guesses, right? That's the point. But that was like what, yeah. So you want autoregressive, but autoregressive is pretty expensive. So we're like, okay, we could use a single layer, but single layer by itself isn't good. Oh, once we try the Medusa thing of like using the features that are rich, having autoaggressive single layer, so it can condition on if we pick this word, use this one more. And if we pick this word, we know we should change the distribution. They shouldn't just be independent guesses that we randomly just call all permutations. We should exploit the ones that are more, yeah, like we can condition on next word predicted. That makes sense? Yeah? Yeah. General, yeah. Again, I don't know super details. Again, kind of high level survey. Wow, that's a lot of text. What does it even say? This is equal to. So all these are using this draft tree structure. This draft tree structure, this is doing it too. Right here, when it says make or help, it just does both. It like does both. Does tree masking, I think, with the speculative even. Can you do that? Yeah. And then you do the next one. You can do that as well. And then you pass that entire tree to be verified into your your main model. That's normally how it works. You have the speculative model. Even with the 7B or whatever, you can have this generate a tree, and then you can verify the tree with the main model. Because if you just did one sequence, if the one sequence messes up and it fails on the first one, you're screwed. But if you do a whole tree and you do this masking, maybe the first token fails, but you also in the same time in the one pass when you pass this through, you check the second token. The second token actually did hit, and then its first token and that didn't hit, but the third one did, right? But you're checking all of them at once. So in one forward pass, if one fails, you can hopefully one of the other pass down the tree got you the longest sequence length. And hopefully it can be like at least like a couple tokens, and then like, oh, I got a sequence length of like 3 I can verify. That's 3x speed up. That's amazing, right? So yeah, Medusa does independent. The basic idea, you can use a smaller model, kind of hard, you have to mismatch. You can use Medusa, which is independent heads. Eagle's kind of cool because it does the single transformer layer and it incorporates the features. And Eagle 2 is kind of interesting in that how we were exploring this tree before, we were technically just going like top 2 and splitting evenly. But as they say, however, this assumption appears to contradict the insight of speculative sampling or speculative decoding, that some tokens are simpler and be predicted by smaller models, right? So what they do is they say, wait, actually, if let's say we have this word it, and we're gonna pick the next word, it is or it has. If we have it is, and that has a higher probability from our draft model, we're gonna assume they found this to be true, but the assumption is that also means there's a higher chance of our main model actually accepting it. Maybe that's not true, but they found it's pretty obvious. Like if your smaller model is trained to be like your big model, if you have a higher confidence in it, it's probably higher confidence in being accepted, right? So the main idea is that we have the word it, we have is and has, and what we can say is, okay, we're actually going to exploit this side of the tree more. We're going to explore and draft more potential outcomes from this. Because the reason is, let's say now we have this tree structure and we're back to the main model. So we generate this tree of all the possibilities from our small one really, really fast, really like quick guesses, you know, and then we're going to verify it with our main model. The point is, if the main model does align with this probability, and let's say it just has a higher chance to choose this one more, we should not spend more time in our speculative generation of the tree on this branch, right? Because it's a lower probability the model chooses it. Let's say this tree was even perfect. It's a sampling procedure, right? Let's say our model, once we got to the main draft, like our main model to verify the tree, it had exactly these probabilities. It still has to pick a word to actually choose, right? So even if the draft speculation is exactly what the model is, you still want to do the thing of exploiting the higher probability paths, because that will be a higher probability that the model will actually pick when you generate. Yes, Will?
I noticed you, in the text it says top 2 longest sequences. Does that mean like, should that be the top 2 most likely sequences?
Yes, you multiply the probability. So like 0.6 times 0.8 is probably the highest, and then 0.2 times 0.7, right? The 0.6 times that isn't that bigger. This one isn't bigger. So these are the 2 that you want to expand. So you have a tree. You want to expand these 2. So what you do is you then expand these by 2, right? And then you re-rank and you say, okay, and that's my new tree. Okay, where do I want to then expand that? Right? It could be that you even go back up to here. Let's say all these, like, because it's less than 1 you're multiplying. At a certain point, these are all going to be really low probabilities, right? Because the chance of you picking this, then this, then this, then this is really low. So you might eventually, the top two paths might be like back up to here and then spawn another branch, right? So it's.
Yeah,
This
this is just like beam search. You're searching by highest probability. Like you're
Yes,
you're
it-
expanding the highest probability. lead.
it is, yes, you're beam searching.
But you only expand the top two, so it's not true that you're like I guess beam search would do theoretically you expand all of them, like all the
No,
probabilities.
beams you do too. Oh, but you don't throw it away. That's
Yeah.
the difference.
Yeah.
You're not throwing. Wait, is beams you throw away? No, yeah, beams you throw away. Here you're not throwing away. This is like shortest path or something. I don't know. Like you
But you
keep,
do throw away like the low probability stuff, right? Like you remake them and you don't verify the stuff that's like low probability.
no, you keep everything in the tree. Everything is in the tree. Like it has a low probability, but you generated this.
But
Hey,
if you
keep
look
it around to verify. Like, why not? It has a chance. But what we want to then decode next off of, that's undecided.
Oh, I'm just looking at like your flat to 1D thing. It looks like your flat to 1D thing doesn't include the low probability like parts of the tree.
Doesn't, let me see, B or to do? No, it does B. It doesn't do. You re-rank. Yeah, I guess it, oh, you're right.
It's like the 8 most probable stuff.
Yeah, okay, so when you're expanding, you're doing top two. You're doing like these most like, I don't know, probable paths that you expand. And then when you actually verify, you don't do all of it because it's maybe a little bit too much. I think you could, I mean, you should shove it all in there if you wanted, but it's just a way to re-rank. Yeah. But anyways, tree masking, it's really cool. You can speculate multiple paths with tree masking, and your speculation can be with not a whole transformer, it can just be like with a single layer that you like fine tune. It's pretty cool. Yeah.
Is tree masking like a boost training thing? Like, do you just like, I don't know, take the zeros out afterwards and then just like find it, or do you like put the sparse vector into like your MLP?
You literally just set the attention mask at inference. Yeah. It's like a post-training, like you can set the attention mask to be whatever you want. Right.
Does it not like, I don't know, I feel like if you
No.
train with like a poll thing and then you put in like a bunch of. the
So
sparse
it's actually it's no different, right? Because
like,
this being here, this check mark being here or here, it doesn't affect it. It doesn't affect it because
Wouldn't like the vectors be more sparse, even like.
No, mathematically it'd be the same. It's just like we're still like I guess like in the really long context, we are still doing like a full like autoregressive representation, right?
Yeah.
So like it's like the has can like a sense of like the token, or has can sense the has. That's
So then wouldn't there be like zeros and like, for example, if you look at the vector, it's like now we have, instead of having 1, 1, 1, 1. it'll be
no,
like-
because like the attention mask is applied after we calculate the attention source. So
Yeah,
like,
yeah, yeah. But then you put in like the rows into the MLP, right? So you just have a bunch of zeros in it.
no, because we do softmax.
Yeah. So what you do is you on a single row, you accumulate all these, or you do attention scores, and this is 0. So this is gonna multiply 0 by the is vector, and then this is gonna multiply some amount by the has vector. There's no difference if it happened here or here, right? As long as these two have the same positional information of the next token, it doesn't matter.
But after the attention.
Oh, yeah, you switch the sequence.
Like you multiply that like the value vector until you collapse like that there. So it
Oh.
Like, I don't know, like x equals like 5 times 0 plus 8 times 0 or times 1 is the same thing as like, I don't know, like same thing as like x equals 5 times 1 plus times 0, I don't know, plus
We're 25 minutes long.
times 1. Oh my gosh, plus 1.
We haven't-
Okay, we gotta speed up, yeah, okay. Wait, that's it. Okay, that's pretty much it. And then look, see how this you can use to speculate. You kind of get it. Look, this is kind of like Eagle. It's a single transformer block. That's what they did. It's pretty much Eagle. Look, they say it somewhere. Look, they say Eagle. This is the multi next to prediction. They say Eagle. It's pretty much Eagle. Yeah, they do Eagle, but they do it in pre-training. In post. Okay, cool. DeepSeek-R1. This is we're just gonna go over entire RL. Let's just do that real quick. Yeah, okay, I'm gonna go in, how much do you need? 15? I'll give you, wait, so I'll go 5. I'll do this in 10-15 minutes. Okay, sounds good. So, this is PPO. This is how we do that like loop. This is how we do that loop of training the model to learn the reward. Why do we have to make this so complicated? We don't really. We're gonna see that. But the technical reason is that, like, let's say we output a generation, and then we want to then have a text and we want to reward it. You can't backprop through that because you like sampled the text. Sampling is a non-differentiable operation. You don't know how to, there's no gradients. There's no way to do that. So how OpenAI did it in RLHF is pretty much like, okay, we're gonna actually treat this like a reinforcement learning thing, and the output of the text is like a policy model, like an agent in an environment taking an action, and then we have the reward as like the reward for that action, and we can iterate and use proximal policy optimization to optimize it. Okay, cool. What this actually means in implementation land with PPO is they have a lot of different terms and things, but the general idea is this thing called the advantage. Just think of that as like the reward. That's like the generally the reward we give it. And we're saying, okay, what you want to do is pretty much given a question, right, that you get, and the output, this O, which is sampling based off the question, what is the output, right? That's like, it's all complicated math. I don't know why they do it. Whatever, it's like, because they want to formalize it. But the point is, you sample a question from your data set, you get an output from the model. You then say, okay, I'm going to get A. What is A? A is this thing and stuff down here, and there's some other stuff and more complicated. But generally, A is just the reward for that output. And then we say, okay, we want to maximize the reward. And then this is saying, hey, don't deviate too far from your old distribution, right? It's just kind of like normalization. You don't want to go too far. That's how I'll explain it, right? It's a ratio of your old policy versus the new one. You're about to update. This is like what you're going to go to. But if you're going to update and if the update goes past some clipping range, you're like this one token. It's like, I want you to say like happy more, right? But you really wouldn't say happy. And you say happy like 100 billion times % more than the previous ratio, then you're going to get clipped. I'm not going to let you do that. It's too big of an update. So we clip the updates, but we generally move it in a direction that rewards the good outputs, right? Larger scope. Let's look at what this means. So we have the policy model. We have a question. We give it to our model we want to train. It's the model we want to train. We get the output. We then need to reward this output, right? So we pass it through a reward model. This is the one we train to mimic humans, and we get a reward. And then we do some other stuff, and we get the advantage. Technically, I've been lying to you. The A, this is a lot of complicated. Oh, this is a lot. I don't know if we can do this in time. The A, this could just be your reward. We could just say, like, we're going to give you your reward. But what we actually do is we say, we're going to do the advantage. Why? What is advantage? Advantage is technically your sum of future rewards minus the expected reward. The point being this reduces variance. Like that's the general idea. Advantage is like, I would think about it as like just a way of like, it's variance reduced reward, right? Because let's say you're good. You're doing good. Hey, I should reward you. But on average, compared to what I think you should get, you're actually worse. We shouldn't give it positive reward. Even the reward is positive, even the reward is good. If based on our expected value, your reward is actually less than it, it should be negative, right? So the advantage is the advantage based off the expected amount, right? But how do we get this expected amount of like how good you are answering this question? That's a very easy question, right? We have to get expectation, right? So that's the value model. This is a whole other LLM. So in this process, we have 3 LLMs. We have 4 LLMs actually, but for now we've talked about 3. It's insane. This is like massive amount of memory you need to use. We have a question, we sample it from our model, we get the output, we get the reward from it. This is an entire neural network that learns to like score your things. We then also get another model that says, okay, the value model, what do you think the actual expected reward is? And then we compute, ignore this, it's pretty much the advantage, which is this, which we say, okay, we want to get how much the reward you actually got, which is the R, which is Q. That's pretty much R and Q are the same, right? For now. And then the V is the expected amount, right? So that's the A. That's what we give it by. So if you did better than the expected, you get a positive reward. If you did less than expected, you get a negative reward, right? But in this PPO formulation, all this, we need this like value model to give the expected to reduce variance because we want to do like a relative amount. So that means we also need to train this guy while we're using that advantage to train this guy. These two are frozen. This reward is frozen. And I didn't even mention one more other model that we have to have, which is this reference model. This is at the very, very, very beginning. What we do is, I don't think it has it even here, does it? Oh, it has it in the, ooh, I don't think we have it.
It's in the log.
It's in the, right here. For now, I'll just like hand wave it. But we have this term as well. Ignore that we got rid of the value. I'll show you in a second. But this term is in the loss. But in PPO, we also have this term. This term says your reference model. This is the model you initially have. And we say you will get penalized if this is tail divergence. This is it's a function which tells you how different probability distributions are. So what you do is say, hey, we have this reference model, this model which we initialized from. Now we're training this other model. And if our trained model's prediction is way farther away from our original model, we penalize it, right? And you're like, wait, didn't I say that before? So looking back at this old is referring to in a single iteration when we're doing one update based off our previous update and our next update. Is it too much of an update? And then we also have this auxiliary loss, which is as we're doing this update between models, which is between these ratios of the old and the current model, which we're updating. We also have this other loss term, which is saying the very beginning model, how likely is it under that? If you start deviating too much, you're just going to get penalized for that, right? This is mainly to stop like exploitation and things like maybe you just want to spam the word good. And maybe over time you slowly learn good, like spamming one word because that gets high reward for some random reason. We're going to penalize you a lot, right? So we make sure weird behavior like doesn't happen. If you're gonna increase the reward, do so, but try to make it as close to the distribution of the original model as possible. Yes, well. Yeah.
Actually, can I explain this from the RL perspective?
We have 4 minutes. I don't think we're trying. Yeah. So that's the general idea. Cool. Technically, the advantage is an advantage. It's like the weighted sum of all temporal differences. So like technically that, and you weight all of them, and that's what that advantage is. But generally, just think about this. It's you subtract the value to reduce variance. You need that value model. Okay, cool. What GRPO does is called group relative policy optimization. They get rid of the entire model. Yay! These are all 175. Like let's say your GP3. That's 175 billion parameter model. 175 billion parameter model. Reward model is also probably 175 billion parameter model. 175 billion parameter. Oh my gosh, that's so much memory and so much running of models, and this is crazy, right? So they say, hey, get rid of the value model. Just sample a bunch of them, sample a bunch of outputs, and get the rewards, and then just get the mean. And the mean is your expected value. You don't have a neural network sitting there and estimating your expected value return on the question and then training that as you're going. Just sample a bunch and just subtract the mean. Like, what are you doing? You know? So they get rid of entire model right here. It's no value model. And nothing else changes. It's pretty much the same. They move the loss around and stuff. But the general idea is we do these little iterations of increasing the advantage. And the advantage is literally this simple term. It's literally no complicated RL, no nothing. Literally just get the reward that you have, subtract it from the mean rewards, divided by the standard deviation rewards. If you're better than your group, increase that. If you're worse than your group, advantage is less, decrease that. And then you just have your standard, okay, don't deviate too far from previous little iterations and don't deviate too far from the original. That's it. We got rid of the entire model. That's what GRPO does. Cool. Skipping over that, reward model. Yeah, okay. So technically, again, this is a model, right? So these you get. This is just a normal LLM. This is also just your original LLM that you keep a frozen copy of. Technically, people use a neural network. You train it on like reward pairs and stuff. And like you can do stuff where you verify step by step, where you don't reward, this is rewarding the entire output. You can like outcome reward models, you can reward each step. And then you can do like output of each step and yada, 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 right? Who cares? Okay. I think, yeah, this is actually DeepSeek math. This is where GRPO was introduced with the math, and they used a neural reward model. So this right here, that was a neural network. Okay, cool stuff. It's overcomplicated. I really don't know why they have it. Okay, this is DeepSeek-R1. Look, they use GRPO. It looks exactly the same, right? No, the difference is they use a rule-based reward system. We do not apply the outcome or process neural reward models in developing DeepSeek-R1. They don't use it. So back to this image. This is not a neural network. This is like a single line of code saying, did it match the label output? Did the code compile? That's it.
Like how long is the response?
How long is the response? Yeah, that's about it. Actually, no, I don't think it.
Oh,
No, they literally just do, did it get the answer, correctness, and did it format in the right way? That's it. they don't use a neural reward model because they found it reward hacking. Like I said, if the neural network really liked the word good, it could be exploited by just spamming good. And we try to stop that. But it's like, why are we using another adversarial neural network? Just throw out the neural network, just directly train on verified stuff. For reasoning, for like toxicity and whatever, you kind of, it does go up, right? But you get rid of it. So now it's just all you do is you have two LLMs. You have your original frozen one and you have the one you're training. And how do you train it? You just reward if you ask a question and you sample 64 outputs and you reward them on this one compiled, this didn't, this did. If all of them compiled, then they all get 0 because on average you didn't improve. But if one of them compiled and all of them didn't, oh my gosh, you're really good. Like you have a really standard deviation away, we're gonna reward you a lot. That's it. That's it. That's all we do. That's what it does. And look, wow, DeepSeek-R1. Look at that. Ooh, it learns to like increase context length. It learns to increase in reason for longer. That's cool. It scores as good as OpenAI 01 on a lot of these benchmarks as well. Oh my gosh. Right? Amazing. Again, it's the same DeepSeekV3 base model. They just tuned it in this way of just reinforcing the outputs which did better. Right? And then this is another thing, cool, whatever. This is another thing, whatever. Yeah, that's about it. They did, wait, where am I? Oh, does this not show the, yeah, let me get rid of this. Yeah, they have a distilled model. So they pretty much distilled it also from the big model into like these other dense models. You can run this on your like laptop with a llama. I literally run 14B and sometimes like 7B. It's okay. Pretty crazy. Yeah. That's it. That's it. And then Jordan, you have now 14 minutes.
Okay.
That's a lot of
Okay, 40 minutes totally. Okay, so our team talked about how DeepSeek and just kind of like a lot of the LLMs leading up to it has been trained. But here's is one very small math problem I want to give to you. Let's take a look at a model like even just like Llama 405B, right? There's 405 billion parameters. If let's say each value in your parameter is just 1 byte. We don't even think about FP32. It's somehow we're training an FP8, right? It's just 1 byte because FP8 is 8 bits, which is 1 byte. How many gigabytes will the model take? It's just storage wise.
405.
405 gigabytes. And what's the largest GPU that we have right now? Like in terms of VRAM.
H200, 140 gigabytes.
And is 140 gigabytes less than 405? It is. So we have a problem. We cannot fit a single model in a single GPU. What's our solution? We want to spread it across multiple GPUs. But how the heck do we do that? That's the sort of secrets of how they actually train these LLMs. And then these techniques have been here since like 2019 to like 2021. These have been here for a very long time because the thing is, the moment you go past like 20, 25 billion parameter LLMs, you start to have problems with this because when you're training LLMs, and this is back in the days when they only had 80 gigs in their biggest GPUs, H100s, right? The things that are in your GPU is not just the model itself. That's only a part of it. When you're training, you're also keeping track of every single one of the layers activations. And also as you're doing backpropagation, when you're doing gradient descent, you're keeping track of the gradient itself. And if you're doing, say, like Adam, you not only are you keeping track of a copy of the gradients, which is the same exact size the model parameter, because you need a gradient for every single parameter, right? You also need to keep track of the variance of the gradients, which is also on your GPU. So the GPUs, like how much storage the model takes up on the GPU really matters. And GPU parallelization is how can we reduce that? So I want to begin with data parallel. So what data parallel is, like the very naive, just like data parallel, is that we have, say, you have a batch size of 8 that you're training, or like 16, like some multiple of 8. Like, okay, let's say 16. You're training something, you have a batch size of 16. You have 8 GPUs. All data parallel says is let's just split that batch size of 16 evenly across each of the GPUs. So each GPU has a local batch size of 2, and then we get their gradients and we just kind of accumulate the gradients together by summing it together. That's the idea. It's very simple, and then you may ask questions like, well, there are layers that within an LLM, like normalization layers, which actually normalize across batch sizes. What do you do in that situation? And the solution to those is either you have 2 choices. The first choice is you can try to do some weird GPU communication thing where you're like syncing the mean standard deviation across different GPUs so the different batches get mean standard deviation information from each other. You can do that. That's a lot of overhead. In reality, people just say, it's fine. It's fine. The local batch sizes are going to be big enough that it's fine. In the long run, like we're going to get good enough gradings anyway. So that's data parallel. But the problem with data parallel is that reduces the sort of overhead of activations, right? Because like in this case, your activations are only going to be, because activation scales with batch size, right? If you have a batch size of 2, that's going to be twice the amount of storage you have to keep track of when you're doing backpropagation compared to a batch size of 1, right? So you have reduced the size of activations that's actually being stored on your GPU, but then your model is still really big, right? So this is where FSDB comes in. It basically says this. As you're training, and this is usually with like models where you can very easily separate them into different layers, and transformers, that's the case because you literally just have transformer blocks that are entirely separate from each other. What you do is, let's say I am at a layer 1 right now. When I'm at layer 1, I really only need the weights for layer 1 to be in my model. Oh, sorry, to be on my GPU. So every single other layer, I don't need those weights right now, right? I only need layer 1's weights to be across every single one of the GPUs. And for layers 0, 2, 3, 4, 5, every single layer that I'm not executing right now, spread out these weights, like just take all these weights and divide them into 8 portions, and just spread them out in all the GPUs. We call this process sharding, which we talked about. The process of sharding is you take just some tensor, you want to divide it evenly, as evenly as possible as you can, across all your GPUs. And basically, to kind of reiterate, FSDB says, when I'm not executing all these other layers, spread all these weights out into all your GPUs. And only the layer that I'm actually doing execution on, accumulate them together, to concatenate them back together, because I need the full weights to actually do my computation. And that's the idea. And FSDB was something developed by PyTorch, actually, and by Meta. And one of the things they also say is, oh, this sort of like when we're trying to, like, let's say I finish executing layer 1. Now I need the weights of layer 2 to all be gathered together, right? If I do all of these sequentially, like I finish layer 1, I wait for layer 2, like all GPUs communicate with each other, put all the weights back together, I execute layer 2, and then like maybe I have to wait for layer 1 to spread them back into the GPU. That takes a very long time. That's where GPU communication is much faster than GPU-CPU communication, but it's still much slower. And like you still have the overhead. The idea is just, why don't we just do that asynchronously, right? Because when you're doing GPU computation, you're not communicating with the other GPUs. The bandwidth of inter-GPU computation is open. So what you can do is, as you are doing computation on layer 1, you say, I want to pre-fetch all the weights for layer 2 back into my GPU. I want to pre-store that into my GPU. And as you're starting to do computation for layer 2, first you asynchronously put the weights in layer 1 back as you're finished doing layer 1 stuff. And then you start prefetching layer 3. So this sort of like parallel, like almost pipelines situation. Yeah, yes.
So like in pipeline parallel, like an issue is that you have to like do your full forward pass before you can start doing the backwards pass, right? Is FSDP also plagued by that problem?
So pipeline parallel is a different thing. I'll get to that. But the idea is that, okay, when you're doing this, you do your forward pass, and then in your backward pass, you can do like the reverse direction of like, doing all the sharding and non-sharding. And there's certain like optimizations you can make of then the sort of like part of the optimization that you make is one of the choices you make as an ML engineer is, how do I group my layers, right? You can say just, every single transformer block is sort of like my one stage of, FSDP sharding. Or you can do even like, you can group multiple of these layers together if you want to reduce the sort of prefetching overhead. And these are all choices you have to make depending on what the delay of inter-GPU communication is, how fast it is actually to compute, like one layer in a GPU. And these are all just like, what is your hardware? Do you have like NVLink that's able to have inter-GPU communication very easily, or do you have much slower connections that are actually across servers or like across different nodes? And these are all things you have to benchmark and you have to test. But the main idea is this sort of like asynchronous, as you're computing one of the layers, for all the other layers, you just spread them out on each GPU, and it's before you go to the next one, you just, put them back. So you basically, with very minimal overhead, you can achieve a much better memory reduction. That's the idea. Does that kind of make sense of what FSDP does? What they call a fully sharded data parallel, because you're sharding all the weights when you're not using them. Okay, does that kind of make sense, FSDP? Cool. So here is the problem. Oh, wait, actually, before we talk about that. So another thing that works very well with FSDP is activation checkpointing. So the idea of like when we're doing normal backpropagation, if you think back to like, okay, if we have a linear layer, it's like Wx, so we ignore the bias part, it's just Wx. Then the gradients of the loss with respect to your weight would be something like the gradients of the loss with respect to the output of that Wx, and then times like x W transfer, like something like that, right? Like basically the point is when you're doing backpropagation, you need three things. You usually need the current weights of the model, which we already have in the GPU. You need the outputs, like the physical output, the physical inputs and outputs, usually only the inputs of when you're doing the forward pass. And you need the actual like gradient that's been passed through in the previous layer. So here's the main thing. You have to store specifically your input and output. You have to store those activations. And those activations add up in size very quickly. Because as you're doing the forward pass, what you have to do is, okay, I'm going to illustrate this real quickly. I threw this together in Google Slides yesterday. But basically, imagine your blue stuff as weights. And like each of these is like a transformer block, for example. And you have like sort of your like pink things being like the activations you're storing. When you're doing your forward pass, in the normal situation, so without activation checkpointing, what you have to do is you have to say, okay, I have to keep a copy of all my activations as I'm going along. So when I'm doing my backward pass, I can actually use those activations to calculate gradients for each of the weights, right? That's very costly, especially when your model gets really big, your activations gets big as well. So what activation checkpointing says is, don't save those intermediate activations. So they take out a lot of space just sitting around the GPU. Instead, recompute them during the backward pass. To illustrate, so instead we kind of group our sort of we group our layers into big groups, and in transformers, very intuitively, this can be just like each transformer block. And you only store the activation at the end of each of these groups, kind of illustrated by the yellow block here. In the forward pass, you just only store those activations. There's much fewer activations you're storing. And during the backward pass, you say, okay, I'm going to redo my forward pass again, but this time I'm going to actually remember what my activations are. Then I'm going to do the backwards, right? And after I've done the backward, I've done the gradients for this layer. I can throw away those activations. I don't need them anymore. Do the same, redo the forward pass again. And then I do my backward pass, and then again, I can throw away the activations. It's a very simple idea, but by doing so, you have drastically reduced the amount of activations you actually have to store in your GPU. And you may be like, well, that seems like a huge amount of overhead. You're redoing this forward pass thing, in backward pass. But the beauty of this is we're making the assumption that the forward pass is much, much shorter compared to the backward pass. And that is almost always correct in machine learning. Is optimization takes way longer, and because it's way more expensive than just doing the forward pass. And we're using that fact to say, even if we're doing this, essentially we're doing forward pass twice. We're doubling the amount of overhead for forward pass, but that's not a huge amount in the grand scheme of things. And that's how, so activation checkpointing at the cost of a tiny amount of overhead from having to redo essentially forward pass one more time, you're able to save a lot of memory in terms of not having to actually cache your activations. Yes, Will.
Why is the backward pass more expensive? I mean, you're just calling like the backward function.
Right. Usually the reason why backward pass is more expensive is because when you're looking at the gradients from the previous layer, like you're actually multiplying. Like another thing is activations themselves are usually a smaller matrix than the actual weights of the model. But then when you're doing your backward pass, you're multiplying it with the gradients of the previous layer. And it's just like that's usually a bigger one. And also another thing is the gradient of the previous layer is usually per batch size. Like you have a gradient for every single one of the elements in your activation. So when you're doing this, that's much bigger than just doing the forward pass. There's certain reasons why that's the case. I think if you actually look at the matrix math that's happening, like there's just more stuff happening in the backward pass than there is in the forward pass. I don't think I have a great answer for that, but that's again, like at least in my own experience. Like for example, if a forward pass takes like 1 second, forward plus backward is going to take 10 seconds, right? So like in terms of just sheer time, like forward pass is usually much faster. Yeah. Okay. So that's activation checkpointing, and you can kind of see how this can work very well with FSDP, because when you're doing your backward pass, like you don't really care what the whole activation stuff. You only care about this little bit. So like the fact that you can drop these activations is really nice because you don't, as you shard them, you don't have to worry about also sharding the activations themselves. You can just shard the model weights itself. So like this works very well. Like with FSDP. Now here's the problem. FSDP has diminishing returns because even with activation checkpointing, even with all these stuff, When your model gets really, really big, your activation the size of your activation starts to overpower the size of your model itself. Sometimes your model is just so big, has so many dimensions, that even with FSDP, and even with a batch size of 1, like a local batch size of 1, you still can't fit it in your GPU. And this will happen with big enough models.
Can't you also shard the activation?
You can shard the activations, but at a certain point, like there's always overhead of like the things you have to store there. Even when you shard it, you still can't fit it in, even with a batch size of 1, because you can't split a batch like just this one single element gets even further. Well, model parallelism says yes, we can. There's other reasons. I'll talk about why model parallelism exists, but the idea is that most of our operations, even including convolutions, have some sort of denseness to it, aka some linear layerness to it. Like if you just think about a normal linear layer, right? If we have, what we can do is instead of just doing, like y times x, sorry, like a times x equals y, what you can do is you can actually split up the x and your weights itself, do these computation completely separately, and just concatenate it together to get your final answer. Linear layers just allow you to do that. You can just split things up, do the computation separately, and concatenate them together.
Very key values, yeah.
Kind of like, yeah, exactly. So we have this like idea basically, and then when we have activation functions because they're per element, you just apply them anyway. So using this to our advantage, we can say, well, why not do these computations in separate GPUs, right? All of a sudden, what you have is, because you're computing them on different GPUs, you're having the amount of memory, right?
Sorry, I wasn't paying too much attention to the FSDP part, but like in FSDP,
Yeah.
do you like also shard, do you like split a tensor with sharding? Or do you just split?
You don't split a tensor because when you're doing the actual computation itself, you have to take back all the weights.
Oh, right.
Yeah, okay, yeah. That's actually the reason why I want to say this, is because when you're in FSDP, when you're executing a layer, you're still taking back all the weights together. So sometimes a layer can still be too big to fit in the GPU. That's the reason. That's what I was messing up. So just to clarify, yeah. So it's like even a layer sometimes can be too big to fit in your GPU, and this is what you do because you can split. Yeah.
Like you still need an all gather operation, right?
Yes, you still need an all gather operation. That's pretty slow, right? And for this one, basically what we can say is like, oh, like for example, just with an NLP, you can do this separate. You can separate it across 2 GPUs, for example. You do your 2 NLP layers, and you just put it back together with a sum.
Wait, so like FSDP, you had a shard. Couldn't you isn't this just operating just with that shard technically? Is that what this is like doing?
Kind of. You have to be very careful the dimension you operate your shard on, and sort of like your data dependency of how that's happening.
Sharding is general, but
Yeah.
in like the class of sharding, like this could be a sharding. You keep
Exactly. Like for example, like PyTorch's now implementation of FSDP, which is with torch stuff distributed, and that's how they like deal with distributed tensors. The back ends for data parallelism and model parallelism are the same. They are inherently the same idea of you're splitting up things across different GPUs, but it's the dimension in which you're splitting on. This you're splitting in the dimension of like tensor, whereas that you're splitting in the dimension of data.
Yeah.
And that's different, and which is why these two can be combined together.
Is model parallelism? Is this tensor parallelism?
Model parallelism and tensor parallelism are usually kind of used interchangeably.
Okay.
Model parallelism also includes something called pipeline parallelism, which is that you can put different layers on different GPUs.
Yeah, like the first one.
Right, and you just kind of pass things in between them. So that's the third dimension, which is why the ultimate goal for training these is what we call 3D parallelism, which is data parallelism, which is what we talk about with FSDP, combined with tensor parallelism, which is mostly what we're talking about here, and then pipeline parallelism. By doing parallelism across all 3 of these, we can achieve a very much lower memory usage, obviously at the cost of additional communication overhead because you have to do communication across GPUs here. But the great thing about that is when you're actually training these models, remember you're training on big servers, and servers, the way that they work is you have nodes. A node can have say like 8 to like 32 or even bigger, like some number of GPUs. And in those GPUs inside a node are usually literally physically linked together. They are linked together with physical hardware, something called NVLink, for example, right? So communication within a node between different GPUs is really, really quick. However, when you go beyond the node, like a lot of times you're doing multi-node training, and in those cases, training, you actually have to communicate across node. That's much slower because you're going to say like gigabit like Ethernet. So what you can do is, because model parallelism does communication way more frequently, you do model parallelism within a node, and then you can do data parallelism across nodes. Okay.
Whoa.
Yeah. So by doing so, which is why a lot of these things, there's no one answer. It's like it entirely depends on what hardware you're training on. What's the network topology of all your models?
But
all you
DeepSeek-V3 had all this detail.
Yeah, they definitely have all this detail of how they manage to do this. They actually do more advanced stuff like this,
Yeah.
specifically with like GPU kernels that we're not sort of talking about. Anyway, okay, yeah, that's model parallelism. Yeah, that's the end, I think.
Go back to
So so from my experience using parallelism at my internship, Python parallelism is basically non-functional in PyTorch distributed right now.
Okay.
I've wrangled with it for a very long time. It's just not. Currently in PyTorch distributed, you can very easily get to 2D parallel with enough wrangling and work. Python parallelism is very much experimental and it's very, very limited because you have to, like, to get efficient Python parallelism, you have to do basically what DeepSeek did, which is go on into like the kernel, CUDA. Yeah, like you have to build up bidirectional bridges and do like all this stuff to actually make it work. Like if you look here, most of these like they talk about precision, right? But they also talk about communication hardware, compute hardware. They have to talk about this because this justifies the choices they make when they're doing parallelism, right? And you can see like dual pipe computation, communication overlap. This is all about like the details of, okay, we are doing all these parallelism stuff. How can we best do that? Given that we have, these limitations, this is how we manage to figure it out. Yeah. Which is why training DeepSeek, as much like there's a lot of like computer science and machine learning to it, there's a lot of engineering too, because a lot of parallelism is actually engineering work. It's figuring out how we can actually make this happen on real hardware. And everyone's real hardware is different. So yeah, okay, I think that's the takeaway for parallelism. Okay, I think that's the end of the reading group. Yeah, cool. All right. Nice.
Stop recording. Stop recording. Stop. How do I do it? Stop share? Yeah, stop.
Yeah.
How do I do it? Wait, just stop
yeah.
share.
You stop share and just stop recording. You're gonna have to like trim the video anyway.
Yeah, wait, can I don't
Yeah, yeah, square. Yeah.